Okay, some updates to the schedule. Dr. Carlson and myself, and me, we had a discussion regarding the following the rest of the semester. So we are trying to give you an option for this guy. So these are not too. There's no programming involved. You know, this is just the soldering and testing. It's a hash code will be given to you, and this one you can use this one to replace the PCB assembly if you want. If you really don't want to make a PCB out of the project, you have the option to use whatever outlined in Lab 15. No programming still, okay? Pretty mentally simple, I think. But it's very important. He said you guys are going to use it for the following classes in the future. That's what he said. So, you know, originally I was planning on having these calculations of the angles of the accelerometers in the lectures. I was trying to use both these two lab time for you to work on your project, but seems like we can only have one here as an option to let you work on your project. So you have to use your spare time to get it done. So I'm still giving you time to work on it because we're trying to make a compromise here, which is having this lab as an option, right? So you can either do this, no coding, again, it's pretty simple, I think. A lot of calculations and contents for the accelerometer, how the registers work. I've done a lot of experiments with this accelerometer in the past. So we'll cover the details over here and probably give you a in-class exercise over here because they will be on the final exam. Just prepare you for the final exam. And then on Thursday, we'll go to the lab. If you don't want to fabricate a PCB and assemble it, you can use whatever you assembled over here and test something out. So if you go to the website, you can see there are 4 options. 1, 2, 3, 4 different sort of projects, like door counter, vibration analysis, step counter. So these are just signal detection, right? You got an accelerometer signals come in. You can count the peaks to count how many steps are there. So no coding. I think the code is provided. So no pressure, okay? And this is a very important sensor, super popular. It's called MEMS. In the engineering field, MEMS means micro electrical mechanical systems. MEMS. If you go to graduate school, there are just so many different labs are working on MEMS. You know how that works? How the little tiny chip can sense acceleration. It's amazing. I had I still have that guy in my department in Phillips College. So he used to work for Sandia National Lab, and they fabricated all these MEMS. So these are actually little tiny silicon wires, and they fabricated one on top of each other. So whenever it moves, it's actually a very little mechanical system inside the chip in the micro nanometer level are moving around. So when it moves, it changes the capacitance, and that capacitance change will be digitized as a C2D, so CDC, C2D converter, capacitance to digital converter. So eventually get the data out. So that little chip, you can see how small that is. It's amazing. So it's able to directly output I2C signal, which is a standard communication protocol. A little bit more complicated than UART, but similar stuff, just serial, one wire for data, one wire for clock. Okay, and eventually we'll have our lab manager to have all the parts for you guys. It's gonna be ready in the lab. So on November the 14th, you come to the lab. I believe the boards, the parts will be ready on the bench. I'll make sure that works since I'm gonna do it first. And make sure no problems, okay? So what's gonna happen is you have the parts, the boards, and you place all the surface mount components on the board and put in the oven, and it's gonna solder all the parts to the board. Pretty fun. And you'll have a accelerometer. I think the board you are going to solder is gonna be a charging board. a battery charging board, supply power to this guy. You know, I have a better design. I'll let you take a look at it. No, they're both good designs, but this is just more industry level. Let me show you. So if you look at this one, right? So we did it and we put it into the microcontroller class as well, very similar to whatever Dr. Carlson did for you guys. So you guys are lucky, it's good. And you can see we are trying to fit that sensor to the horseshoe. So that's the little holder to hold one cell LiPo battery and the sensor itself. Why I want to bring this up? Because it's a very similar idea. If you just look at the big daughter board in Lab 14, it's probably still not that necessary. I think, why do we still need a one cell LiPo battery? If you look at this little very limited area at the bottom of the horseshoe, now you can tell. Why just one cell LiPo battery? You don't have the room for two. So which means it has to be low power and it has to be 0.0 volts, because one cell LiPo battery is providing what? A very good interview question. That's why Dr. Carlson's lab is really good, because it's teaching the same thing what I'm teaching at the 4. So what's the voltage for one cell LiPo battery? What's the voltage? I mean, this is not common, but you should know as an undergraduate in electrical engineering. 0.7 volts, one cell, it's standard. 2 cells, 7.4 volts. 3 cells, 11.1 volts. Standard, okay? No changes. Interview questions. Okay? If you don't have the room, you can only use one cell. Okay? One cell. So that means all the devices are 3.3 volts, and you only have like 400 millivolts to drop, which is pretty challenging for analog design. What does that mean? Because you got battery power supply as 3.7 volts, right? And your devices immediately need a 3.3 volts. So there's only like a 400 millivolts loss is allowed through the regulator. But usually the regulators are losing, for the ones on Arduinos, these are losing like 1.2 volts. It's like 50 cents regulators. So all these analog designers in TI, in analog devices, they're smart enough to design, it's called LDO, low dropout regulator. Let me show you. So you can talk about, so after you assemble that daughter board in Lab 14, you can tell, during the interview, you can tell them, I used LDO, right? LDO. Why? Because I can only use a one cell LiPo battery, one cell LiPo battery for what? To supply 3.0 volts for the microcontroller. Okay? Because LDO is low dropout voltage regulator. Right? Dropout means from like 3.7 volts, it's going to drop after the regulation inside for the output. So I think the one you guys are going to use is, I don't know, I didn't see the numbers, but definitely it's working, right? So 0.7 volts is able to, so you are able to use that 0.7 volts to get a 0.0 volts out. Okay, so this little thing has a ESP32, has a 2-core CPU, 32 bits, and with a Wi-Fi wireless capability on that. So eventually this is a little accelerometer. You can see how small that is, and that's the LDO. So the LDO has to be tiny as well. We found out the LDO like $5 a piece from TI, soldered on it, and you can see all the resistors are 0603 instead of the 1206 surface mount that we use for our PIC board. So that's why I'm telling you guys the 1206 they're huge, even though they are surface mount components. But compared to the 0603 ones, these are the smallest ones I can solder by hand. And there's a charging board you can connect to it. I think we are going to do that for Lab 14 as well. So it's a really good lab. So it's charging up the battery at the same time, powering up the chip or the system. So it's a different charging circuit, but the one I use is it has a battery battery in and eventually voltage out. So the battery in, whenever you connect the power source to the charging chip, it's going to charge up the battery, but not interrupting the power supply. So actually, it's very similar, right? So if you grab a smartphone, it's really practical. When you are charging your phone, you couldn't like make a phone call or watch the YouTube videos, right? It should be able to be operated at the same time, right? When it's charging up, you should be able to use it. So you need a charging circuit that has a chip on it, and we are going to find out how that works from the one Dr. Carlson designed. But that's a really good lab. So for this one, we have to make it small. So eventually, the IMU sensor sensing the acceleration and the gyroscope, which is the angular speed velocity, can be fit into this little box, and we designed a feature which is called twist and lock. So insert and twist, so it locked into at the bottom of the horseshoe, which is over here. And so we mount it to the horse, and it output data to the AI model. So deep learning model eventually will be able to find out if there's laminates or injury of the horse joints here. So that's the goal of this project. But I can tell why we need a low LDOs, right? Why we need a one cell battery, and all this kind of story. It's all super practical and reasonable. So now let's take a very quick look at it, just in case. Right? So you can see this lab has all these like calculations and the things Dr. Carlson want to convey to you guys are really good things. I will cover these in the lectures and give you some in-class exercise or or put in the exam. Okay, make sure you guys know all these details. These are 1206 surface mount components, and I've just found out a link inside in here shows the details. But anyway, so lab 14 doesn't have programming tasks. Just directly download the hex file and use it. Okay, collect the data, answer the in-lab questions. Done. So it's mentally easy, but really practical, practice hands-on soldering skills. Okay? Any questions on this? So lab 15, because we already posted the pigboard PCB, and I think a lot of you guys really want to do it. So that if you want to keep working on that PCB part, you'll be fine. If you still don't know what to do with the PCB and you don't want to make a PCB out of it, definitely do lab 15. Okay? Do lab 15. So everyone has to do lab 14. So you have to assemble a IMU board. It's required because you have to use it for future labs. I forgot the name of like seed lab or something else, senior SEM, whatever. So you have to use it, okay? So everyone has to do it. But for lab 15, for the testing, measurement, analysis, it's an option, okay? If you don't want to do a PCB, assembly, soldering, fabrication, it's okay. So just do lab 15. We are not going to change task 1 and 2 since it's already announced, scheduled. It's not hurting anything, right? So you got to learn how to use Eagle. So it's going to be just the Eagle file, you post it, I grade it, but we don't have to fabricate it if you decide to do lab 15 instead of starting the PCB. What's that?
So to clarify all this, the PCB design spec is still due, the recreation of the board, that's still due?
Yeah, that's a PCB file, right? So you are submitting the PCB file for task 1 and 2. It's already announced, we cannot undo it. So that one will be, it's due Wednesday this week, right?
I just wanted to clarify. Yeah. And then there is there's lab 14, which everyone will do. Correct?
Yes.
And then there is lab 15, which is either that or the project?
Either that or the PCB part of the project.
Okay.
But the project is still on I'm sorry, say it again.
No, yes.
Yeah, so the project is still 20% of this class, right? The project 20% of the class, and that one you can demonstrate everything on the dev board or on the breadboard instead of the PCB. So you're still getting full credits if you replace the PCB task in the project with the lab 15 report. Make sense?
Okay.
Just more options. I think it's good. It sounds like complicated, but actually it's giving people more options.
Could you, in somewhere on an assignment, like post this just so that, like in an announcement, so that if we get confused, we can look back and know which project?
Yeah, I'll do that.
Okay.
Yeah.
Thank you.
Any questions on this? Is it getting better or getting worse?
Well, one more extra lab.
Huh?
It's fun.
One more extra lab, yes. One more extra lab, which is the soldering. No coding, but soldering. Yeah, I just have to do it.
I guess it makes sense if it goes into the next class too.
Yeah. What's that?
We could get it drop lab grade.
Yes, one. Yeah. So I don't know how that works in Canvas. I can explore that, right? How to let students drop a lab, but instead what I can do is, since I heard all the other professors are letting students drop 2 or 1, I was thinking about 1 for now. So the way we can do that is I'll just you let me know which one you want to drop. I'll just give you 100 on that. Both in lab and lab. What about that? Okay, that works.
So that was my question. If it was for in-lab and out-lab.
Yeah, for both. So it's just one of the labs, both in-lab and lab, I'll just give you 100 on it. Okay? Okay? So, yeah, I was thinking spend more time on the project, but it seems like the department really wants you to work on these two. So let's just do it. I have no other options to replace this, but I think these are good. So let's just work on it. Okay. So today we are going to talk about Lab A and inLab08, the questions. So and let's see, 21st. So ADCs, right? Then lab, then SD card. Okay. I2Cs. Okay. It's all good. So first, the video I showed you in here for the demo, could you tell me where that signal comes from? That's the sound wave of my whistle, right? Okay. So are these from the ADC or from my whistle or from the LPF, which is low pass filter on the board? So, yeah. So this is a digital oscilloscope. Okay. So when you are probing an analog voltage. Can you probe a digital voltage with 8 bits? Just one pin, right? One pin. If you want to probe like more bits, this is my my oscilloscope. I know how to use the digital version of it. So there's a digital probing capability. It's a bus. It's a bundle of cables, like 16 bits. You can probe like 16 bits at the same time and display all the digital signals in the monitor. But however, just one pin, like these analog probes, it's just probing 1 voltage, right? There's no way that I can probe a digital signal with like 8 bits. Okay, so this is the analog signal, and this is directly from where? From the low pass filter. And there's some math required in the in-lab version of Lab A, so I think I have to cover it so know what's really going on. I have to do this first. Look at the schematic. Tell me what's going on here. That could be an interview question as well, but it's very simple, typical. Inverting or non-inverting? Inverting configuration, because the signal comes into the inverting terminal of the op-amp. So what is this guy doing here? What is this guy doing here? What is this guy doing? What is this guy doing?
Yeah, TI asked me that too.
Yeah, this is removing the noise, right? Remove noises. Capacitor will couple the AC noise and short it to ground. So the AC noise will short to ground. Why do we want to short AC noise to ground? You want to make DC stable. Low ripple for DC. Ripple? Heard about that before? Ripple? So DC voltage, right? There will be a little ripple here. And you want to get rid of that. Okay? Steady DC voltage. So what's the voltage here? Look at the resistors. 10K, 10K. So what is this? VCC, so the logic high in this pegboard is what? 3.3 volts, right? That's logic 1. So VCC is 3.3 volts. And being divided by this voltage divider, 2 resistors. Let's just look at the DC part because AC part is being removed. So just DC part of it. So DC part of it, 3.3 volts DC voltage, getting divided by this voltage divider, and you are getting how much voltage here? 1.65 volts, 50% of the voltage. Why?
Resistors in parallel with the same resistance.
Oh, they are not in parallel, it's in series. Right? It's power supply and running current to the ground. It's forming one loop. It's a loop. So it's in series resistor. It's a voltage divider. So here's 50% of the voltage of VCC. So why do you need a 50% of the voltage here? So that's why it's a little bit disconnection from the microelectronics classes and the practical cases, right? So in circuit 1 or any other electronics classes, in the lab, we directly use this 15 and minus 15, right? And we got a signal here, V in, ground. Okay? No problem, because it's a dual power supply. So your signal V in is allowed to what? To swing around 0 volts. It's gonna swing around 0 volts. So this is the 2 rails, the ranges. So your VL is gonna be nicely a 180-degree phase shift, but getting amplified, but still around 0 volts. The center is 0 volts. 0 volts, 0 volts. The AC signal is sitting around 0 volts. Use superposition theory. AC signal comes in, DC voltage being supplied to here, added together. So eventually it's still AC signal swing around 0 volts. Okay? So if I do this, it could be an interview question. If I do this, is this a correct schematic or no? And why? Why?
If it's grounded to 0, then it can't swing around.
Can't swing to the bottom, right? So what's gonna happen?
It'll just get to its region.
You're gonna cut off, okay? So because it's a inverting configuration, so what's happening is it's gonna be this, because the negative part won't be amplified. You don't have the range to let it swing. Okay? But however, for our circuit, for the pegboard, do we have a minus 15 volts? No. Right? You don't have minus 15 volts. For 99% of the circuits, you don't have negative 15 volts in there. So why do they still teach it? Okay? You randomly grab a op-amp circuit from the end of the textbooks, it won't work in the lab. This works. We know that works because I whistle and amplify it, right? So look at the practical circuit here, Dr. Colston design over here, okay? It works. What you want to do if you have this? Can you imagine, like when you are doing the interview for circuit design job, you don't even know how to simplify a signal using op-amp. See? Okay, so yeah, it's very common. It's very common. It's very common. Okay, so what you want to do here? It has to be grounded. You don't have anything else. It has to be grounded, right? You just lift it. Just lift it. Give a signal here called VCM. VCM is common. It's called common mode voltage. So in our circuit is a voltage divider circuit, like a VCC. Get a resistor, another resistor, grounded. So 10K, 10K. Why 10K? Why not 10? It's not a yeah, it's not drawing too much current. It's not a functioning circuit. Just dividing the VCC to 2 halves, right? Why do you need like 10 ohms and drawing like 100 milliamps? You just need the voltage. You don't need the current. Okay, this could all be interview question. So VCC divided by 2 halves, and you are getting what? 1.65 volts, right? So that voltage will be superimposed to here as the DC voltage. So your signal will swing around 1.65, which is 50% of the range. So you can swing in between 0 and 0.3 volts, which is exactly what the power supply has on the board. So the whistle will be this, okay? If it's getting amplified, it will be amplified around 1.65. So it's really nicely swinging around in between the two ranges. This range, not two range, one range, okay? Any question on this? Now let's look at this guy here. What is this guy doing? A capacitor. You got a signal and it's blocking the signal. It's blocking the signal, right? So is there still anything arrives here? Why?
Because some goes through, some doesn't.
Why do we want a capacitor in front of it? The signal hit a wall. What is passing? AC. So capacitor is the AC short circuit. Okay? Capacitor can pass AC. Do you know why? Have you thought about why? Why AC signal can pass? It's a disconnect circuit. Why AC signal can pass? Is it really passing? No. What is actually happening?
Just low impedance.
No.
It's like drawing current back and forth, so the current almost
Yes.
gonna draw charge.
Yeah. No current really running in here, right? So what's happening is whenever this part getting charged up, what's happening? It's attracting negative charges. However, don't think about that way. Think about the other way. Whenever you got, so for example, on two plates, right? One side of the plate, it's charging up, okay? What's happening to the other side? Charging up with positive charges. What's happening on the other side?
Negative charge.
Negative charge. Also what? So negative charge comes in, what is going out? Positive charge is going out. So what's really happening? Your charge up is repelling positive charges on the other side. Okay? So it seems like it charged up. On the other side, the positive charge is also going away. So it seems like it's passing. But nothing is actually passing. Make sense? So capacitor can pass AC. That's how that works. But for DC signal, it's steady voltage, no current going back and forth. No current. If you so no current, no voltage, right? So if there's no current, it's not going to draw any movement of the charges. So nothing is moving here. That's why you want to place what's the name of this guy though? When you see a circuit like this, what's the name of this part? Oh, so whenever you get a sensor, it's sensing analog signal from the real world. Okay, it could be a sound, could be temperature, could anything else from a sensor, right? It has an arbitrary DC offset. What does that mean? So when I'm talking, definitely my voice as a signal is a kind of AC signal, but it's based on a DC level. So if you directly display my voice over time, it actually has an arbitrary DC level, has my voice over here, okay? And that DC level, depending on different people, it's a different value here. It could be like 1.2 volts, 0.5 volts, whatever. Okay? So if you directly fit this into the op-amp, what's gonna happen? You don't even know where the signal is gonna swing around, right? It's changing. Like you have this as a range, 0.3 volts. This is the signal, right? You want to amplify it by 20 times. What's going to happen? Here, definitely got amplified, but here, cut off, right? So no room to swing to the back or to the bottom. So what's happening is you want to remove the DC offset first for whatever sensor signal from the analog world, okay? Remove the DC first, all the time. See? This is called a high-pass filter. High-pass filter passes high frequency, which is the AC part of it, and block DC, which is low frequency. DC is gone, so only AC part will pass. And then this one is being superimposed to it, so you are making a uniform DC or VCOM or VCM in here. So your signal will be lifted to what? 1.65 volts here, being weighted for what? For getting amplified by the amplifier, right? So what was these two guys doing is first, could you tell me? I think here probably needed I need some clarification on this resistor, on this 12 resistor. Anyway, it's probably required by this microphone for some reason. Anyway, but you know, we only look at this high pass filter. So first it's getting high pass filter, DC offset getting filtered, and then being lifted by 50% of the range, and then being amplified. Any questions on this? Okay, and then it's followed by what? This is a low pass filter. This is a low pass filter. Why low pass filter? Because there probably are some high pitches with high frequency noises of the input. Because you didn't block high frequency, it's a high pass. So high frequency comes in, you want to remove some of the high frequency noises. It's not your signal, not your voice, it's noise. Okay? So these are being removed by this low pass filter. Why is this low pass filter? I'm going to derive it. It's important for one or two of the questions in the inLab. You just need to know where that comes from. Okay. So first thing you need to know, if you don't look at this part, what is the DC gain? Are you familiar with that term? DC gain. DC gain. Low frequency gain of this amplifier. What is the low frequency gain of this amplifier? How do you find it? For example, I got a low frequency signal here, okay? Is this one doing anything for DC signal? Is this capacitor doing anything? Remember how that inverting amplifier is designed. It's just simply an RF feedback resistor, right? That's it. That's an inverting amplifier. Okay?
Gains R
Now,
over R1.
yeah, R9 over R7 is the DC gain. What does that mean? If you plot the V out over V in, so what do we care about for the amplifier? The frequency response, yes, and also the gain, right? That's what we care about it. That's why we use it. So V out over V in, which is the gain, if you plot in the frequency domain on the y-axis, is a gain, no matter what gain it is, because the frequency domain has all the frequency components. Okay? For low pass filter, what kind of frequency response you can expect?
You get lots of gain towards low frequencies and less gain towards high frequencies.
Mm-hmm.
It's like,
If I have a capacitor here, okay? If I tell you this is a low pass filter, what's going to happen is, right? Low pass. Okay? Low frequency, pass. High frequency, attenuate. Okay? If I don't have this guy, what's going to happen? Oh, definitely there's a frequency response inside as well. There are capacitance as well. So eventually it will drop. High frequency will drop. But anyway, for this one, you can find out a specific, you can design a very specific FC, which is called corner frequency. If during interviews they ask you for the corner frequency, what's the attenuation at the corner frequency of the signal?
minus 10 dB.
Minus 3 dB. How this is derived, I'm going to show you really quick. Okay? All right? If I move for 10 times the FC, how much I'm degrading here? If there's like 10 times FC, it's called decade. 10 times, 10 years, a decade. So this is, if I move 1 decade for the frequency, how much attenuation here for the low pass filter like this? It's minus 20 dB. I'm going to show you why, okay? If you don't know why, just directly use it. It's better not wasting your time. It's not helping at all. So I'm going to draw that schematic really quick. CF, it's RF, R1 VI, VO. So that's a simplified schematic. And this could be a little bit boring, but I'll do it really quickly, okay? So the impedance of the CF is 1 over J omega CF. Remember in circuit 1? 1 over J omega CF. Why is that? Because whenever omega is 2 pi F, right? So when F is higher, omega is higher. When omega is higher, your impedance is lower, so the capacitance is lower. Okay? And the overall resistance over here is 1 over J omega CF in parallel with RF. Okay? And over R1 will be the gain minus, because that's the equation of the inverting. Okay? So that's VO over V in. So VO over V in is 1 over J omega CF times RF over 1 over J omega CF plus RF. That's the parallel resistor equation, R1. Okay? So I'll directly just get results for you instead of wasting too much time on this. So this eventually becomes minus RF over R1 times 1 over 1 plus J omega RF CF. Okay? So if I do a amplitude of this gain, because the gain is just amplitude, no phase involved. So that will be RF over R1, that's just a constant, times 1 over, you can find out the amplitude of this imaginary number, which is 1 plus 1 square plus omega RF CF square and square root. Okay? So 1 square is still 1. So one of the inLab solutions of the questions is incorrect. So I'm going to show you why is that, because you have a DC gain here. So that becomes 1 plus what? We can convert this a little bit, because we know omega is 2 pi f. Okay, 2 pi f, which is the frequency of the signal. Okay, omega is a radians per second angular velocity, and it's 2 pi f. So we can replace this with 2 pi f times RF times CF square. Okay, very close, almost getting the result right now. And this equals RF over R1. 1 plus. So I'm going to show you how to do it, okay? This is somewhere like having a lot of fun, because you start understanding, oh, that's really what's going on, how we get the minus 3 dB stuff, the bandwidth, just everything, all the questions, all the mud got cleared in your mind. So if we keep F on the top and divide it by 1 over 2 pi RF CF, it's still an equivalent expression. Do you agree with that? Because F divided by 1 over 2 pi this, flipping this to the top, it's still the same thing. Agree? Okay? So what is this called? You'll see this in the inLab questions. What is this called? So now you know where this comes from, right? It's asking you, what's the corner frequency of this low-pass filter of this LPF, the low-pass filter? What is it? FC equals 1 over 2 pi RF CF. Why is this a corner frequency though? Why is it? So first is by definition. So if I show you this equation, it's called transfer function sometimes. If I show you this equation, could you let me know if it's low pass or high pass? If this is not given. This is the signal's frequency. This is the corner frequency of the combination of R and C. Like, you cannot change. It's already designed the circuit. I already drew the circuit like this. Already determined the feature of it. So here's the transfer function of that circuit. Okay. Could you let me know? So what is this? This equals VO over VI. Okay. Could you let me know if this is low pass or high pass? how to look at it. This is a constant, right? Can we change it? No. If f is larger, sometimes way larger than this corner frequency, what's going to happen? This term becomes what? Almost f squared. Okay? Sometimes this frequency can be a lot larger than this. So this becomes just a pretty large number, okay? And plus 1 is nothing compared to like a mega, or like a 10 mega. Ignore 1, okay? So if you get a higher f, you are getting a higher or lower gain here? Lower, why? Because higher f, lower gain, right? Higher f, lower gain. High pass or low pass? Higher f.
Low pass.
Low pass, because higher gain, higher frequency, lower gain, right? So it's low pass. Make sense? And whenever f equals fc, what's going to happen? VO over VI equals what? In this case, it has the DC gain here. We have to keep writing it, but a lot of times the DC gain is 1, so we don't have to write it down here. Anyway, it's just a DC gain. Keep copying to here. What is this? If f equals the corner frequency, right? We're plotting this guy. When f equals fc, we got a minus 3 dB here. Let's see if that is true, okay? So usually, because the number here is pretty large, so usually we use logarithm values, so convert it to 20 times log. So for this one, 20 times log 10 based, okay? 20 times log of this guy becomes 20 times log of RF over R1 times what? What is this?
1.
2, because
1 plus 1.
yeah, 1 plus 1 is giving you a square root of 2. Okay? So what is this? It's 20 log what? RF over R1, which is the DC gain, right? Cannot remove it. Plus 20 log okay? So you have that logarithm calculator here. So 1 over this is 0.707. Okay? So let's do a 20 times log of it. Log, 0.707 log is this, right? Okay? Times 20 is what? Did you see? What is it? Minus 3 dB. That's the unit for 20 times log. So this still not changes the DC gain. Okay? If the DC gain is 1, it's the 1 here, so you are getting a 0 here, which is RF over R1. Sorry, R1, not RF. So now you let me know what the DC gain is over here. What is the DC gain? So no capacitor involved, right? What's the DC gain?
9 over R7.
Yeah, so it's 1 mega divided by 10K, right? Is what? 100. So DC gain is 100. Yeah, DC gain is 100. So this one is a negative 3 dB, and that's the DC gain. You have to separate it. So in one of the questions is asking you if the frequency, for example, I'll just directly give you a number. If the frequency here is 10 times larger, what is the gain, overall gain is? If here is 10 times larger. Remember, I showed you? If you got a 10 times larger of the frequency, what's happening? you got a minus 20 dB drop. If that's true, let's take a look at it, see if that's true, okay? 10 times larger, so we're getting 10 times square 100 times, okay? 100 times plus 1, no, don't do that, tiny, so ignore it. So 100, square root of 100 is what? 10. 1 over 10 is what? 0.1. Plug in here, 0.1. 20 log 0.1 is what? So log 0.1 is what? Negative 1 times 20 is what? Negative 20, what? dB. Make sense? 10 times larger the frequency will cause a 20 dB drop in your frequency response. So in the inLab question, it tells you, hey, for example, 0.3 kHz, 0.3 kHz is giving you a, for example, this is a frequency response. I will just show you the curve, show the plot here. It's more straightforward. Instead of giving you examples, just look at the frequency response over here. Okay? So the first question is asking you, from here, what did you read from this curve?
No gain until.
Oh, sorry, this is the speakers, I think. Wait, let me see. Oh yeah, that's the speakers frequency response. Speakers, microphones frequency response. Okay, so yeah, no significant drop until 20 kHz, right? Okay, so for human hearing range is typically between 20 to 20 kHz, so this works perfectly, right? And if it tells you that 3.3 kHz, could you find where that is? Is there attenuation for 3.3 kHz?
Zero gain.
Mm-hmm. Yes, over here. It's not changing, right? It's not changing. So I think it should actually provide that AC signal here. I don't think 0.3 kHz is the correct signal to give as an input, because it's flat. It's not on the ramp here. So it's on the ramp. It's going to be 20 dB minus 20 dB attenuation. Just let you know. Okay, if you see that, but still treat it as 20 dB attenuation. However, the thing is, you just have to know there's a DC gain. There's a DC gain still existing, even though this is attenuating by 20 dB. Okay, or in here it's actually 10 times smaller. But however, since you have 100 times DC gain, so eventually it's still amplifying by 10 times. If the frequency is not attenuating, what's a DC amplification gain for this circuit?
100.
100. If the frequency is not attenuating, or the signal is not attenuating, it's 100 times gain, because it's 1 mega divided by 10K, right? It's 100. But however, when it moves to this domain, starts attenuating after the corner frequency here starts attenuating. Every 10 times of frequency, every 1 decade, will give you a 20 times dB attenuation. Keep that in mind. So this is what's really happening. Okay, if you see different problem descriptions, you still know how to deal with it. All right. So that's everything I want to talk about for the math over here. On Wednesday, we'll go through the details about the Lab 8. Other questions. There are just a lot of questions we need to clarify. Okay? All right. See you on Wednesday.